November 16, 1951. The morning fog slowly lifts off Portsmouth Harbor, revealing the looming silhouette of the HMS Illustrious. The crisp air hangs heavy with anticipation as Captain Dennis Campbell ascends the gangway, briefcase in hand. Inside, a single sheet of paper rests, a seemingly simple diagram, its lines drawn with quiet purpose. A flight deck, angled 10 degrees to port. To the untrained eye, it appears no more complex than a child's sketch. Yet, in the span of the next 18 months, this small piece of paper will change the course of naval aviation forever. What Campbell doesn't know as he steps onto the ship that day is that this diagram, so simple, so unassuming, holds the key to saving more lives than any weapon system ever invented. But the stakes are grim. In the past year alone, the Royal Navy has lost 43 aircraft to landing accidents, 43 machines destroyed, 17 pilots killed, and many more maimed. Each tragic loss has happened during those final desperate moments of flight, the landing. For the men flying in the jet age, the margin for error has become razor-thin. The same fate haunts the American Navy, where the death toll is even higher. The sky has become a deadly battleground, and the flight deck, once the symbol of hope, has turned into the most perilous place on Earth. But today, Campbell will try the unthinkable. The early 1950s marked a transformative period for naval aviation. The jet age had arrived, but the carriers, those vast floating airports that supported naval power across the oceans, were designed for propeller-driven planes. By the end of World War II, jets had begun to replace the slow-moving piston fighters. But while the technology of aircraft advanced at a rapid pace, the carriers and their landing systems remained mostly the same. The design of the aircraft carrier, particularly its flight deck, was a relic of an earlier era. In the 1940s, the average aircraft was a propeller-driven fighter, like the F-4U Corsair, which landed at speeds of 70 knots. The propeller-driven engine allowed pilots to chop the throttle just before landing, gently falling onto the deck. But jets with their powerful engines didn't work this way. Jets, like the F-9F Panther, which entered service in 1950, flew 40 knots faster than their propeller predecessors and needed to maintain power right up to touchdown. This was a deadly problem. Jets couldn't abort their landings once they were committed. Their engines took 7 long seconds to spool up from idle, an eternity when a plane is hurtling towards a small landing zone on a pitching and rolling deck. If a pilot missed the arresting wires, the result was often catastrophic. Without enough room to maneuver, the plane would slam into the steel barricade or, worse, into rows of parked aircraft. Fires, explosions, and deaths became a regular occurrence. By 1951, the U.S. Navy was grappling with a devastating series of accidents. The statistics were alarming: 776 Class A. Mishaps, defined as accidents that either destroyed an aircraft or resulted in the death of the crew, had occurred in the previous year. That was more than 2 per day. The numbers were even worse during the Korean War. On the USS Boxer, 7 barrier crashes were reported during one deployment alone. The USS Princeton lost 9 aircraft in just 4 weeks. On straight-deck carriers, missing the arresting wires meant one thing: disaster. The situation was no less dire for the British Royal Navy. By 1951, they too had suffered numerous fatal landing accidents, with pilots dying at an alarming rate. The small margin for error was further amplified by the inherent dangers of carrier operations. Pilots were expected to land on a 60-foot-wide strip of steel while dodging a steel barricade behind them and rows of parked aircraft ahead. A single mistake, a single miscalculation, could lead to tragedy. By this point, it was clear to anyone involved in naval aviation that the carrier landing system was broken. But what could be done? The solution seemed elusive, and the problem was more than just technical. It was a matter of life and death. As the Korean War raged on, the stakes grew higher. The U.S. Navy's carriers in the Pacific were being pushed to their limits, operating in an environment that was as unforgiving as the planes they launched. The arrival of jets on the scene had revolutionized aerial combat, but exposed the vulnerability of carrier operations. Jets had fundamentally different landing characteristics compared to their propeller-driven predecessors. The physics of the situation were brutally unforgiving. A jet like the F-9F Panther, landing at 125 knots, covered a staggering 201 feet per second. This was too fast for the existing arresting gear and landing procedures. The arresting wires, originally designed for slower planes, were not able to handle the immense energy of these jets. On the straight decks, when pilots missed the wires, they were forced to hit the barricades or plow into parked aircraft. The consequences were catastrophic. Even when the arresting gear worked, it was a matter of luck. Captain Bruce Williams, serving as the air operations officer on the USS Kearsarge, witnessed firsthand the horrifying results of a barrier failure in March 1951. An aircraft came in too fast, missed all the wires, and struck the barricade at full power. The resulting explosion killed 11 men, destroyed 14 aircraft, and caused extensive damage. The Navy was facing a crisis, and there was no clear solution in sight. At the heart of the problem was the design of the carriers themselves. The straight deck design, a relic of the World War II era, was now incompatible with the demands of modern jet aviation. This was the conclusion reached by Captain William T. Raseur, a senior officer in the U.S. Navy, who wrote in a report in 1945, "Current landing procedures force all aircraft into a 60-foot impact zone with zero margin for error. This is incompatible with jet aircraft performance characteristics." Translation: the carriers were designed for planes that could land slowly and cut their power at the last moment. Jets, however, were fast and powerful, requiring a different approach. Despite the overwhelming consensus that the current system was inadequate, no one knew how to fix it. Engineers tried building better barriers, and the British experimented with a system called the flex deck, a rubberized landing surface. But nothing worked. The accidents kept happening. The Navy needed someone with a new vision, someone who would question the existing assumptions. That person turned out to be Captain Dennis Campbell, a man who wasn't an engineer, a test pilot, or a visionary by any stretch of the imagination. He was a bureaucrat, a mid-level officer who, on the surface, had little to offer. But Campbell had something far more powerful than technical expertise, a sense of moral outrage. He couldn't ignore the bodies piling up, the pilots who died because of a design flaw that no one had the courage to challenge. He would come to see the problem not as an engineering dilemma, but as a moral one that needed to be solved at any cost. As Campbell stood in the cold, foggy morning of November 16, 1951, with his simple sketch in hand, he was about to propose a solution that would be met with mockery and scorn by the very experts who were supposed to be solving the problem. But Campbell's refusal to accept the status quo was about to change everything. At the heart of every landing was a human life. Pilots, like Lieutenant Michael Lithgow, who had trained for years to land on carriers, trusted their instincts, their training, and their aircraft. But in 1951, those instincts were not enough. Landing on a carrier was a deadly gamble. Every pilot knew the stakes. The fact that they were still flying, despite the odds, was a testament to their courage. For these men, the flight deck was a place of both glory and terror. The final 30 seconds of a carrier landing were fraught with anxiety. The engines roared, the arresting cables loomed, and the wind whipped around the plane's fuselage. Yet it was the landing signal officers, LSOs, who stood at the very edge of this chaos. They were the last line of defense, guiding the pilots with their paddles, trying to ensure the safe arrival of the jet. But with jets landing at speeds that had never been seen before, the margin for error was razor thin. When Captain Campbell witnessed the funeral of Lieutenant Lithgow, who had crashed during a routine landing, the image of the young pilot's widow, 5 months pregnant, haunted him. Lithgow had done everything right. He had the perfect approach, the perfect speed. But in the final seconds, he missed the arresting wires. The barricade failed, and he was killed instantly. This was not an isolated incident. It was the grim reality of a broken system. Campbell couldn't accept this any longer. The death of Lithgow, his student, was the catalyst that drove him to create a solution that would change the future of naval aviation forever. The technology available to the military in 1951 was advancing at an astonishing pace, but the fundamental design of aircraft carriers was still rooted in the past. The straight-deck carriers used during World War II had been designed for slower, propeller-driven aircraft. These planes could land at relatively low speeds, and pilots could abort landings at the last second if they had to. The arresting gear was designed to catch these planes, and it worked well enough for the time. But jets were a different breed entirely. The F-9F Panther, for instance, landed at over 130 knots, much faster than the World War II-era aircraft. The arresting wires were simply not capable of handling the immense kinetic energy generated by the jets. The situation became even more perilous because jet engines took much longer to spool up from idle. If a pilot missed the wires, there was no time to power up and go around. The plane would either crash into the barricade or into the parked aircraft, resulting in disaster. No matter how many technological improvements were made to the barriers or arresting systems, they could only mitigate the damage once the landing went wrong. The problem, as many engineers and aviators understood, lay in the very design of the landing area itself. What was needed was a fundamental shift in thinking, a change in the way the carrier flight deck was laid out. Captain Dennis Campbell was not a man who sought fame or recognition. He was a career naval officer with no engineering background, a bureaucrat by many accounts. But Campbell had a rare quality. He refused to accept the status quo. The world around him was crumbling, and it was his own colleagues, his own pilots, who were paying the price. After the death of Lieutenant Lithgow, Campbell became obsessed with finding a solution. He wasn't an engineer, but he was determined. He began pulling accident reports, talking to landing signal officers, studying patterns in the crashes. He wasn't going to accept the idea that good men had to die for a design flaw. It wasn't enough to fix the barriers or improve the arresting gear. What he needed was a new approach entirely, something that no one else had even considered. The turning point came when Campbell sat down with his notebook on a train ride from Portsmouth to London. He began sketching ideas, trying to find a way to give pilots more room to land. In the crowded space of the train, with only the hum of the engine to accompany his thoughts, Campbell drew a line, a simple one. The flight deck angled 10 degrees to port. Suddenly, it all made sense. The idea was so simple that it felt absurd. But for Campbell, it was the answer to a problem that had claimed far too many lives. It wasn't about complicated technology or complex engineering. It was about the margin of safety, about giving pilots the opportunity to go around if they missed the wires. What Campbell had drawn was more than just a diagram. It was the beginning of a revolution in naval aviation. The resistance to Captain Campbell's idea wasn't just technical, it was deeply institutional. The military, particularly within the Navy, had always been slow to embrace change. And Campbell's proposal, to angle the carrier's flight deck, was a radical departure from decades of established doctrine. It flew in the face of everything that had been carefully constructed since the early days of naval aviation. The idea was initially rejected, outright at a meeting on August 7, 1951, as Campbell unveiled his simple sketch. The room erupted in disbelief. The idea was not only seen as impractical, it was viewed as downright dangerous. The international conventions governing naval aviation required that all flight operations align with the axis of the ship. Angling the deck, critics argued, would violate these established laws, creating more problems than it solved. The naval officers and engineers in that meeting weren't just skeptical, they were incredulous. They were trained professionals, experts in their fields, and to them, Campbell's proposal seemed like amateur nonsense. The thought of landing an aircraft across the ship's natural motion, fighting the ship's pitch and roll, was seen as a reckless gamble. What about drift, they asked? How could pilots possibly land safely when they would have to contend with the constantly shifting deck beneath them? Yet Campbell, undeterred, pressed on. He knew that the existing solutions, stronger barriers, better arresting gear, were just band-aids over a much larger problem. The real issue wasn't the barriers or the arresting gear, it was the very design of the carrier itself. But changing the design was not a task that could be accomplished in a matter of months or years. It was a monumental shift, one that would face immense opposition from the highest ranks of naval leadership. Behind every crash, behind every death, there was a personal tragedy. For the pilots, the stakes were life and death. They knew that a single mistake, a single moment of miscalculation could mean the end of their careers, or worse, their lives. And yet, despite the undeniable risk, they had no choice but to keep flying, to keep landing, because their duty to their country and their comrades required it. Lieutenant Commander Harold Buell, a seasoned pilot, had seen it all. He had landed on carriers countless times, always with the fear that he might miss the wires, that he might crash into the barricade, or worse, into the parked aircraft. The psychological toll was immense. Every time a pilot made a landing, there was the fear of death lurking in the back of their mind. Even if they made a perfect approach, the fear of missing the wires, the fear of being thrust into the steel barricade, never left them. But when Buell made his first landing on the USS Antietam's angled deck in 1953, the weight of that fear was gone. He had missed the wires, and for the first time in his career, he didn't panic. He didn't make desperate, dangerous corrections. Instead, he powered up and climbed away. The open deck stretched out before him, free of barriers, free of obstacles. The second chance that the angled deck offered was not just a technical advantage, it was a psychological one. The relief that came with that freedom was immeasurable. Buell later wrote that landing on the angled deck was sheer bliss. For the first time, he was no longer afraid of dying during every approach. He didn't realize how much that fear had been weighing on him until it was gone. For the pilots who flew after him, the angled deck would become not just a tool, but a lifeline. The implementation of the angled deck would not just affect individual pilots, it would revolutionize the entire strategy of naval aviation. For decades, aircraft carriers had been essential to naval warfare. But their designs, which had evolved slowly over time, had never been optimized for the new realities of jet warfare. The carriers had become bottlenecks, and every mistake on the deck had the potential to cripple a carrier's entire air wing. The angled deck wasn't just a safer way to land, it was a more efficient one. By giving pilots the ability to abort landings and try again, it ensured that fewer planes would be lost due to pilot error. This reduction in losses would translate directly into greater operational readiness. More planes on the deck meant more aircraft available for sorties, more strikes against the enemy, and more flexibility for commanders at sea. In a larger sense, the angled deck would give naval aviation a level of operational flexibility that had never been possible before. Pilots could land and take off without the fear of crashing into a barricade or being unable to go around if they missed the wires. For the first time in history, aircraft carriers could become fully operational with jet aircraft at their maximum potential, not constrained by the limitations of the carrier's design. The turning point came not in a laboratory or a conference room, but on a painted line across the flight deck of the HMS Triumph. The idea was simple. Paint an 8-degree angled line on the flight deck and test it. It would not be a permanent modification, just an experiment. The stakes were high, but the cost of failure seemed worth the risk. If the angled deck worked, it could save countless lives. If it failed, it would be the end of Campbell's career, and potentially the end of the idea itself. September 1951. The HMS Triumph left Portsmouth Harbor, not with a major overhaul but with something far more subtle. A painted outline of an angled flight deck. The concept would be tested not by engineers or committees, but by the very pilots whose lives were on the line. For 3 weeks, Navy pilots would land on the painted deck, simulating the experience of an angled landing without the actual structural modification. The only thing that would change was the deck's orientation. The test was as controversial as it was risky. Some pilots were already skeptical, while others were outright hostile to the idea. Landing on an angled deck went against everything they had been trained to believe about carrier landings. What about the drift? What about the instability of the deck? These were questions that Campbell himself had no answers to, but he was convinced that it was worth testing. The current system was killing pilots. Anything, even a small change, could be the difference between life and death. The first landings on the painted deck were filled with tension. The pilots were cautious, unsure of what to expect. But within days, something unexpected happened. The pilots adapted. The drift that had been predicted, the subtle shift caused by the ship's movement, didn't exist. In fact, it was less of an issue than landing on a straight deck. The pilots found that they could actually focus on their landings more effectively, without the looming threat of a crash into the barricade or into the parked aircraft. Lieutenant Peter Chilton, one of the test pilots, later wrote, "I came in too high, floated past the wires. And for the first time in my career, I wasn't terrified. I just poured on power and climbed away. No barrier waiting to kill me. No aircraft ahead, just clean air and a second chance. The relief was palpable. What had once seemed impossible was now a viable solution. The data was undeniable. The angled deck worked, but the real challenge was yet to come. The concept was one thing. Convincing the rest of the Navy, particularly the U.S. Navy, that this idea could revolutionize carrier aviation was another. In the autumn of 1951, a pivotal moment arrived at the U.S. Naval Air Test Center, Patuxent River, Maryland. Lieutenant Commander Eric Brown, the Royal Navy's chief test pilot, stood before 40 American test pilots. Despite his distinguished career and extensive experience landing on all types of aircraft, he felt the weight of skepticism pressing down on him. The Americans had their own set of established practices, and they were not accustomed to being told by a foreign officer that their entire approach to carrier aviation might be flawed. But Brown had already witnessed the success of the angled deck firsthand on the Triumph. He knew it worked. Now, he had the daunting task of convincing the U.S. Navy, who had been struggling with an unrelenting wave of landing accidents, to trust a British idea. The atmosphere was tense as Brown pinned Campbell's sketch to the wall, the angled deck design now a symbol of defiance against the status quo. The room erupted into disbelief. "You want us to land sideways?" they asked. "What about the LSO? He can't see the approach angle. What about the island?" The objections came quickly, one after another. But Brown, calm and steady, persisted. "We had every single one of these objections in the Royal Navy," he replied. "And then we tested it. Here's what we found. When you miss the wires on an angled deck, you don't die. You throttle up and go around." The room fell silent. This was a radical departure from the long-held doctrine of carrier aviation. For years, pilots had been trained to land on straight decks, where missing the wires meant disaster. Now, Brown was proposing that missing the wires wasn't a death sentence. It was an opportunity to try again. The room was divided. Half the pilots nodded in agreement, while the others, entrenched in their years of experience, were more than ready to dismiss the idea as an impractical British theory. Commander Harold Buell, a senior U.S. Navy officer with a reputation built on decades of experience, stood up. "Commander Brown," he said, his voice steady, "I've been landing on carriers since 1943. What you're describing violates everything we've learned through 8 years of combat operations. You want us to throw away everything we know for a theory?" Brown's response was measured, but firm. "I'm asking you to stop dying for a design flaw." His words hung in the air, heavy with the weight of truth. He knew this was a turning point. The history of naval aviation was at a crossroads, and whether the U.S. Navy would take the leap or reject it would determine the future of carrier aviation. It was then that Rear Admiral Apollo Susk, the senior U.S. Navy aviator in London, stepped forward. "I've observed the tests on the Triumph," he said. "Brown is correct. The concept works. I've recommended that we run parallel tests on the USS Midway." But the room was still far from convinced. Rear Admiral Alfred Pride, chief of the Bureau of Aeronautics, stood firm in his resistance. "We're already testing solutions. The Davis barrier has a 98.7% success rate." The figures were impressive, but they didn't address the deeper problem: the psychological and physical toll the straight-deck system had taken on pilots. Brown didn't hesitate. 98.7% of what? Of the aircraft that hit the barrier? What about the pilots who panic and never make it to the barrier? What about the ones who ditch in the ocean rather than risk hitting the barricade at full power? Your statistics measure barrier performance, not pilot survival. The room erupted in a mixture of agreement and anger. The heated exchange reached a breaking point, and it was only when Admiral Susk raised his voice that the room fell silent once again. "Gentlemen," he said, "we will test the angled deck on the USS Midway. If it works, we'll modify one carrier for full structural implementation. If it fails, we bury the idea. But we will not continue losing pilots to a design flaw we can test and potentially fix." With that, the decision was made. The painted deck on the Midway would be tested. The pressure was immense. If it failed, it would not only end the career of those pushing the idea, but it would solidify the belief that the existing system was the best that could be achieved. But if it worked, The results would be revolutionary. The U.S. Navy would become the next force to embrace the angled deck. It would take time for the full impact to be realized, but that fateful decision would mark the beginning of a new era in carrier aviation. The USS Midway left port, not just for another test flight, but for a historic moment. What happened next would change naval aviation forever. The testing on the USS Midway was a defining moment. By the end of 1951, the results were undeniable. The angled deck worked. The tests were a resounding success, proving that the solution Captain Campbell had drawn on a simple piece of paper could indeed change the course of naval aviation. For the first time, a carrier landing did not end in catastrophe if a pilot missed the arresting wires. The opportunity to power up and go around was more than just a safety measure, it was a lifeline. The success of the Midway tests marked the beginning of a revolution in naval warfare. The U.S. Navy was initially skeptical, but the proof was in the results. As the tests continued, it became clear that the angled deck offered a safer and more efficient landing system. The pilots who flew on the Midway recorded fewer accidents and fewer deaths. The reduction in fatalities was immediate and striking. On the Midway, there were 0 fatalities during the test period, a stark contrast to the tragic death toll that had plagued straight-deck carriers. The more pilots flew on the angled deck, the more they trusted it. It wasn't just about the mechanics of landing. It was about confidence. Pilots could approach with the knowledge that they had a second chance if they missed the wires. This, in turn, saved lives. By 1953, the U.S. Navy made the bold decision to retrofit the USS Antietam, the first true angled deck carrier. This decision was more than just a technical upgrade. It was a profound shift in the way carriers would operate in the future. The transformation was not immediate, but it was inevitable. The U.S. Navy's fleet would soon be equipped with angled decks, drastically reducing the number of landing accidents. The success was not only technological, but psychological. Pilots who had once approached the deck with anxiety, knowing the slightest mistake could lead to death, now flew with confidence. The reduction in fatalities was a direct result of the safety improvements the angled deck brought. But the impact wasn't limited to the U.S. Navy. The British followed suit, equipping their carriers with angled decks as well. By 1955, the Royal Navy had fitted the HMS Ark Royal with an angled deck, further cementing the idea's place in naval aviation. The French and Australian navies soon followed, and by the late 1950s, every major naval power in the Western world had adopted the angled deck as a standard feature on their carriers. This wasn't just a technological advancement, it was a moral one. Dennis Campbell, the bureaucrat who had been told his idea was impossible, had achieved what many thought could never be done. The world's navies had embraced his vision, and thousands of lives had been saved as a result. The success of the angled deck in saving lives was not just an immediate result. It had far-reaching consequences for the future of naval warfare. By the mid-1950s, the data was clear. The angled deck drastically reduced landing accidents and, more importantly, saved lives. The U.S. Navy, which had been the first to embrace the idea, saw a sharp decline in the number of Class A mishaps. Between 1955 and 1957, the number of landing accidents dropped by an astounding 75%, and barrier-related fatalities fell by 80%. In the years that followed, the implementation of angled decks became the standard for every major carrier in the world. For the first time in history, naval aviation was operating at a level of safety that was once unimaginable. The U.S. Navy's new supercarriers, such as the USS Forrestal and the USS Enterprise, would be designed with angled decks from the keel up, fundamentally altering the way naval aviation was practiced. But it wasn't just the U.S. Navy that benefited from the new design. The British, French, and even the Soviet Navy, who initially resisted the idea, eventually saw the wisdom in adopting the angled deck. The Soviets, who had rejected the concept for years, were forced to reevaluate their position after a series of catastrophic landing accidents in the late 1950s. By 1959, the Soviet Navy quietly began retrofitting their carriers, and soon after, their landing accidents dropped by 68%. The numbers told a compelling story. The implementation of the angled deck had saved thousands of lives, reduced operational costs, and improved the overall effectiveness of carrier air wings. The number of aircraft lost during landing accidents plummeted, and the carriers were able to operate more efficiently in combat situations. The change was not just technical. It was tactical, operational, and strategic. Naval aviation had entered a new era, one where safety was no longer a luxury, but a fundamental priority. What is often overlooked, however, is the human cost of inaction before this breakthrough. The pilots who lived because of the angled deck, like Lieutenant James Davidson, who in 1953 made a miraculous landing after experiencing a hydraulic failure, owe their lives to a single moment of clarity from Dennis Campbell. Davidson later wrote to Campbell, thanking him for giving me 142 second chances after missing the wires multiple times. In a letter sent to Campbell's family, Davidson expressed his gratitude. "I never met your father, but I'm alive today because of his vision. My daughter was born last month. I got to be there because of the angled deck. The angled deck saved not only the lives of the pilots, but also the families who would have otherwise been left behind. It was a moral victory as much as it was a technological one. It was proof that one man's refusal to accept the status quo could change the course of history." The story of Dennis Campbell and the angled deck is not just one of technical innovation. It is a testament to the power of persistence, vision, and moral courage. In a world where the status quo was accepted as gospel, Campbell refused to accept that good men should die because of a design flaw. What began as a simple sketch on a train ride grew into one of the most significant innovations in military history, saving countless lives in the process. This breakthrough was not the work of engineers in a sterile laboratory or military leaders in high offices. It came from someone who understood the human cost of failure, someone who had watched too many young pilots die unnecessarily. Campbell wasn't driven by the pursuit of fame or glory. He was driven by the knowledge that the current system was broken and that he had the power to fix it. The angled deck transformed naval aviation, making it safer, more effective, and ultimately more humane. What Campbell did was more than just create a new landing system. It changed the way the world approached safety in warfare. It was a moment when a single idea shifted the course of history, showing that even the most seemingly impossible ideas are worth pursuing if they have the potential to save lives. Today, every aircraft carrier in the world, whether American, British, French, or Russian, uses the angled deck, and it has saved thousands of lives over the years. It's a standard so integral to naval operations that it has become invisible, taken for granted by the very pilots who owe their lives to it. Yet, behind the angled deck lies the quiet legacy of a man who, against all odds, saw the problem and refused to accept that there was no solution. Dennis Campbell's story is a reminder that change often comes from the most unlikely sources. It is not always the loudest voices or the highest ranks that shape history. Sometimes, it is the quiet persistence of someone who refuses to accept that things must always be done a certain way. History remembers the innovators, not for their accolades, but for their refusal to let the world remain the same when they knew it could be better. For every pilot who touched down safely because of the angled deck, and for every family spared the pain of loss, Campbell's legacy endures. The real breakthrough wasn't just the design of the flight deck. It was the courage to challenge the norm and the refusal to accept that the lives of good men should be lost in the name of tradition. And that is the true power of innovation. It is not just about creating new technologies. It is about saving lives, changing the course of history, and leaving a legacy that will outlast the lifetimes of those who dared to make a difference.